Welcome back to G Fun Facts Online. Today, we are not just talking about astronomy. We are talking about the single greatest embarrassment in modern physics, and how, as of late 2025, we might finally be solving it. We are diving deep into a new, groundbreaking study regarding the Milky Way's dark matter heart and the galactic gamma halos that might finally reveal the invisible universe. Let's start with the context, because to understand the magnitude of this news, you have to understand the silence that preceded it. For nearly a century, astronomers have been staring into the abyss of the cosmos, and they realized something terrifying. The abyss is heavy. In the 1930s, the Swiss astronomer Fritz Zwicky was observing the Coma cluster of galaxies. He looked at how fast the galaxies were moving and compared that to the visible mass of the stars and gas. The math didn't add up. The galaxies were moving way too fast. Based on visible matter alone, the cluster should have flown apart like a broken carousel. Zwicky realized something invisible was holding it all together. He called it dunkle materie, dark matter. Fast forward to late 2025. This mystery is still unsolved. We know dark matter exists. We map its invisible scaffolding as it bends light through gravitational lensing. We see it shaping the rotation curves of spiral galaxies. We have built massive tanks of liquid xenon deep underground to catch a particle of it. We have smashed protons together at the Large Hadron Collider, hoping to create it. And yet, nothing. It passes through us, silent, interacting only via gravity. But that silence might finally be breaking. A study from the University of Tokyo, released in November 2025, has sent shockwaves through the astrophysical community. By analyzing 15 years of data from NASA's Fermi Gamma Ray Space Telescope, researchers have identified a faint, spherical gamma-ray halo enveloping the Milky Way. This isn't just random noise. It matches, with eerie precision, the predicted fingerprint of dark matter annihilation. This is the story of that discovery. To understand why this is different from previous false alarms, we need to talk about the instrument. The Fermi Gamma Ray Space Telescope, launched in 2008, views the universe not in visible light, but in gamma rays. These are the most energetic form of light, the shrapnel of the cosmos. They are born from exploding stars, feeding black holes, and, theoretically, the death throes of dark matter. If dark matter particles interact with each other, they should annihilate and turn into pure energy, releasing gamma rays. So, Fermi is our best hope for seeing the invisible. Now, for over a decade, everyone was looking at the center of the galaxy. This is known as the Galactic Center Excess, or GCE. It makes sense, right? Dark matter should be densest in the middle of the galaxy, so we should look there. And indeed, Fermi saw a bright knot of gamma rays in the galactic core, peaking at an energy of roughly 2 to 5 giga-electronvolts, or GeV. For a long time, we thought this was it. We thought we were seeing weakly interacting massive particles, or WIMPs, crashing into each other. But there was a problem. The center of the galaxy is a messy, crowded downtown district. It is packed with supernova remnants, gas clouds, and magnetic turbulence. More importantly, independent analyses suggested this signal wasn't smooth, like a cloud of dark matter should be. It looked clumpy, or grainy. This graininess pointed to a different culprit: millisecond pulsars. These are the undead corpses of massive stars, spinning hundreds of times a second and spraying gamma rays like cosmic lighthouses. If you have thousands of these pulsars packed into the galactic core, they can mimic a dark matter signal. So the community got stuck in a debate. Was it dark matter, or just a bunch of noisy dead stars? The galactic center became a battlefield of statistical models, and we reached a stalemate. This is where Professor Tomonori Totani and his team from the University of Tokyo changed the game in 2025. Instead of staring at the noisy, chaotic center, they looked outward. They examined the halo region. Think of this as the vast, empty suburbs of the Milky Way, extending roughly 50,000 light-years above and below the galactic disk. In the halo, the noise of pulsars and exploding stars fades away. It is a cleaner canvas. And that is where they found it. Totani's analysis revealed a signal that should be there. After meticulously subtracting the known background of cosmic rays and interstellar gas, a residual signal remained. Crucially, it wasn't a clump, and it wasn't a disk. It was a smooth, spherical shell of radiation. And here is the most important part. The energy was different. The old galactic center signal peaked at 2 to 5 GeV. This new halo signal peaked at 20 GeV. This shift in energy changes everything. A 20 GeV peak implies a much heavier dark matter particle than we previously thought. If this signal is from dark matter, the particle responsible would have a mass roughly 500 times that of a proton. That is about 500 GeV divided by c squared. The morphology, or the shape of the signal, is the strongest evidence here. Pulsars live in the galactic disk where stars are born. They do not float in a giant spherical sphere 50,000 light-years above the galaxy. Dark matter, however, does exactly that. According to the standard cold dark matter model, our galaxy sits inside a massive, spherical halo. The gamma-ray signal Totani found traces this sphere perfectly. So let's get into the physics of the invisible. How does dark matter produce light? The term dark matter is actually a bit of a misnomer. It should really be called transparent matter because light passes right through it. However, the leading theory, the WIMP hypothesis, suggests that dark matter is its own antiparticle. Imagine two dark matter particles floating through the galactic halo. For billions of years, they pass each other like ghosts. But occasionally, gravity pulls them together, and they collide head-on. When they do, they annihilate. They vanish from the universe and release a burst of pure energy. Now, this energy doesn't usually manifest directly as gamma rays. Instead, the annihilation produces a shower of unstable standard particles, things like quarks, specifically bottom quarks, or massive bosons. These particles are short-lived. They decay almost instantly into stable particles, protons, electrons, neutrinos, and, you guessed it, gamma rays. These gamma rays have a specific spectral shape, a fingerprint. Unlike the radiation from cosmic rays, which just fades smoothly as energy goes up, dark matter annihilation produces a bump in the data. The energy of this bump is directly related to the mass of the WIMP. The 20 GeV bump observed in the Totani study corresponds to the specific decay chain of a 500 GeV particle annihilating. Why is 500 GeV such an interesting number? Because it fits comfortably within the predictions of supersymmetry, or SUSY. Supersymmetry is a theoretical framework that proposes every particle in the standard model has a heavier superpartner. The lightest of these superpartners, often called the neutralino, is stable and fits the description of a WIMP perfectly. If the 2025 discovery holds, we may have just found the neutralino. This mass range is also intriguing, because it sits right at the edge of what the Large Hadron Collider can probe, which might explain why the LHC hasn't seen it yet. It might just be slightly out of reach, or hiding in a difficult decay channel. But before we start celebrating, we have to play devil's advocate. We must confront the nemesis of all dark matter hunters, cosmic rays. The space between stars is not empty. It is filled with a tenuous gas of hydrogen and helium and threaded by magnetic fields. Zooming through this medium are cosmic rays, which are protons and electrons accelerated to near-light speeds by supernova shockwaves. When a high-energy cosmic ray proton smashes into a hydrogen atom, it creates a particle called a pion. The pion decays into two gamma rays. This creates a diffuse gamma ray glow that traces the gas in the galaxy. Furthermore, cosmic ray electrons can crash into photons from starlight or the cosmic microwave background. When they do, they kick the photon up into the gamma ray range. This is called inverse Compton scattering. The cosmic ray halo is a known phenomenon. As cosmic rays escape the galactic disk, they diffuse into the halo, trapped by magnetic fields. This creates a fog of gamma rays that can look suspiciously like a dark matter halo. So how did Totani distinguish the signal? The key lies in the residuals. The Fermi team has spent years building models of this cosmic ray fog. When Totani subtracted the best fit cosmic ray model from the actual data, the 20 GeV halo remained. If the signal were just misidentified cosmic rays, the residual should have looked like the gas distribution, which is clumpy and disk-like, or like the magnetic field bubbles. Instead, the residual was smooth and spherical. Cosmic rays, which are tied to magnetic fields and gas, struggle to replicate a perfect sphere on their own. However, critics argue that our understanding of the galactic magnetic halo is poor. If the magnetic fields extend further and are more spherical than we thought, cosmic ray electrons interacting with the cosmic microwave background could mimic this signal. This inverse Compton halo is the primary alternative explanation that must be ruled out. This brings us to the universal context. If dark matter halos glow in gamma rays, our galaxy should NT be special. Every galaxy embedded in a dark matter halo should exhibit this faint aura. Our nearest giant neighbor, the Andromeda Galaxy, offers a crucial testbed. Because Andromeda is 2.5 million light-years away, we view it from the outside. We can clearly separate its center from its halo. Previous studies of Andromeda using Fermi data have been mixed, but reanalysis in light of the Milky Way's 20 GeV signal suggests that what we previously thought were cosmic ray winds around Andromeda might actually be this same dark matter phenomenon. Then there are the galaxy clusters like Coma and Virgo. These are the largest reservoirs of dark matter in the universe. However, they are noisy places, filled with hot gas and radio halos. Detecting a signal there is like trying to hear a whisper at a rock concert. But the lack of a strong signal from clusters puts an upper limit on how interactive dark matter can be. The 500 GeV WIMP model proposed by Totani barely scrapes under these limits, keeping the theory alive but under tension. The ultimate arbiters will be the dwarf spheroidal galaxies orbiting the Milky Way. These are old, dead galaxies with almost no gas and no pulsars. They are clean laboratories containing massive amounts of dark matter. If the Milky Way's halo is glowing due to dark matter, these dwarfs should glow too. So far, Fermi has not seen a statistically significant signal from them. This is the biggest hurdle for the Totani result. However, because the dwarves are small, the signal might simply be too faint for Fermi to catch. This is where the future of the hunt comes in. The detection of the 20 GeV halo marks the end of the beginning. We have a signal. Now we need verification. The Cherenkov Telescope Array, or CTA, is set to see first light fully in the late 2020s. Unlike Fermi, which catches gamma rays in orbit, CTA is a ground-based observatory that watches for the blue flash of Cherenkov light, created when very high-energy gamma rays hit the Earth's atmosphere. CTA is significantly more sensitive than Fermi in the high-energy range. While the 20 GeV peak is lower than CTA's optimal range, the tail of the 500 GeV particles annihilation spectrum extends into the tera-electron-volt range. CTA will be able to map the galactic halo with unprecedented resolution. If the halo is real, CTA will see it. More importantly, CTA will be able to stare at the dwarf spheroidal galaxies with enough sensitivity to confirm or refute the dark matter hypothesis once and for all. Complementing this will be the Southern Wide Field Gamma Ray Observatory, or SWGO, planned for the Andes Mountains. It will look at a large portion of the sky continuously, which is crucial for mapping diffuse, extended structures like the galactic gamma halo, which cover too much sky for a pointed telescope to map easily. In conclusion, the discovery of the galactic gamma halo, specifically the 20 GeV excess identified in late 2025, represents a pivotal moment in our quest to understand the universe. For the first time, we have a signal that matches the geometry of a sphere, matches the physics of a 500 GeV particle consistent with supersymmetry, and defies the background noise of pulsars and cosmic rays. If confirmed, this is not just an astronomical discovery, it is a discovery of fundamental physics. It would prove that the standard model is incomplete. It would tell us that the ghost holding our galaxy together is a real, tangible particle that we can study, measure, and perhaps one day understand. We stand on the precipice of seeing the dark universe. The gamma rays washing over our planet are not just harmful radiation, they are messengers from the dawn of time, carrying the signature of the invisible architects of reality. After 100 years of searching in the dark, the galaxy may finally be turning on the lights. Thanks for listening to G Fun Facts Online.